In the previous class, we have seen theory about the worm and worm wheel, applications, terminologies, etc. Now we shall see an example problem. A hardened steel worm rotates at 1440 rpm and transmits 12 kilowatt to a Pasper bronze gear. The speed of the worm wheel should be 60 plus or minus 8 percentage. Design the worm gear drive if an efficiency at least 82% is desired, and also determine the heat generated, required area of cooling to dissipate the generated heat. Here, temperature rise is restricted to 40 degrees Celsius and heat transfer coefficient is given as 10 watts per meter square degree Celsius. First, list out given data. We have been given power P equal to 12 kilowatt, small n equal to 1440 rpm, capital N equal to 60 plus or minus 8 percentage, and efficiency eta equal to 82 percentage, delta T equal to 40 degrees Celsius. Heat transfer coefficient HCR equal to, this is convective heat transfer coefficient, so HCR equal to 10 watts per meter square degree Celsius. First, step 1, selection of materials. Page number 8.45, you can see for the combination of worm and worm wheel, material is given. Material data is being given. For worm, we can select a hardened steel, and worm wheel, for worm wheel, bronze material can be chosen. And in page number 8.45, designed sigma C equal to 1590 kgf per centimeter square with the assumption that sliding velocity is 3 meters per second. Before solving, if it is not given, we have to assume sliding velocity as 3 meters per second. And similarly, in page number 8.45 of the PSA design data, designed sigma B, that is bending stress, limit is given as 900 kgf per centimeter square, and that too for chill casting of bronze. And in the while selecting this sigma B, we are choosing ultimate tensile stress sigma U greater than 39 kgf per centimeter square, and we are assuming that the rotation is in both directions. Next, step 2, calculation of minimum center distance. On page number 8.44, we have been given the formula, center distance formula, that is small a greater than or equal to z by q plus 1 into cubic root of 540 divided by z by q into sigma c whole square into twisting moment, that is designed MT. On page number 8.46, you can see a formula I equal to small z by z, capital Z. And small z is number of teeth on worm wheel. That is not being given in the problem. And z equal to 2 we are selecting Z is nothing but it is start, number of starts. So number of starts we are taking as 2 based on the efficiency given in page number 8.46. 8.46 at the bottom we have been given for the efficiency of 82%, number of starts will be equal to 2. So capital Z equal to 2. And I can be determined from small n by capital N. Both the values are being given as 1440 and 60. And if you divide it, you will get 24 as I answer. And from this equation, small z equal to I into capital Z can be derived, and I is now 24 and number of starts equal to capital Z equal to 2. So 24 into 2, 48. So small z equal to 48. So number of teeth equal to 48. Then for substituting this A equation, we need sigma C. Sigma C already we have taken from data book, page number 8.45. That is equal to 1090 kg per centimeter square. Now all the parameters have been known. So we will directly substitute in this equation and calculate it. And for calculating MT equal to KD into K, MT into KD into K. And for spur and helical bevel etc., we have taken KD into K for 1.3 initially. Here we will take it as 1. So MT equal to 97420 into kilowatt by N into I into efficiency. Here everything is known. So MT equal to 15976.88 kg per centimeter. And designed MT equal to 15976 kg per centimeter. Since KD into K is given as 1 and both designed MT and MT are equal, so whatever value we are getting for MT is equivalent of designed MT. Now if we substitute in equation page number 8.44 for A, and that is center distance, we will get A as 24.63 centimeter. And module corresponding step 11, page number 8.44 for calculation of minimum axial module, that formula is being given as mx equal to 1.24 cubic root of designed MT divided by Z into Q into YV into sigma B. The answer you will get mx in terms of centimeter. And MT is already calculated, and small z also known to us. Q is constant, always it will be Q equal to 11. YV, for calculating YV, since the worm is like helical gear, you refer helical gear page number 8.22. At the bottom, for virtual number of teeth, Z equal to Z by cos cube delta, you use that formula, and Z equal to 48, small z equal to 48, delta is 10.3. How delta is calculated? Tan delta equal to Z by Q. It is given in the page number 8.44, right hand side. So tan delta equal to Z by Q. Z equal to here capital Z. So capital Z number of start equal to 2 by Q equal to 11. So 2 by 11 equal to tan delta. From this, delta can be arrived as 10.3. Delta equal to tan inverse of 2 by 11 equal to 10.3. So if we substitute, we will get ZV, virtual number of teeth equal to 48 by cos cube 10.3, that will be equal to 50.39. Now in page number 8.15, you can see form factors, not 1.5, 1.6, sorry, 1.8, page number 1.8. Form factor table is available. From that table, YV value can be obtained. So corresponding to ZV as 50.39 and under 0 modification coefficient x equal to 0, both the lines intersecting at 0.477, we have to take as YV. So YV equal to 0.477 form factor. Now if we substitute mx equal to 1 point module formula in page number 8.44, we will get module as 4.7 mm or equal to 0.5 centimeter. Next higher value is to be selected from page number 8.2. So 0.47 centimeter. Next to 0.47 is 0.5. That table is available in page number 8.2. Next, step 4, calculation of character center distance. Now, from page number 8.43, you can see a table and it has many formulas, and one among that is A equal to 0.5 mx into Q plus Z plus 2x. Here x equal to 0. Under modification coefficient, it is 0. So A equal to 0.5 into 0.5 into 11 plus 48 plus 0. So A equal to 14.75 centimeter, which is less than A minimum, that is 24.68 centimeter. So to increase, to get a design as safe value, only thing is we have to increase module. Here, if we increase module little bit, from page number 8.2, we will get discrepancy. So the maximum value up to module 1 centimeter can be taken for design of spur, helical, worm, etc. So we have selected module equal to 1 centimeter, that is 10 mm. And if we have chosen module as 1 centimeter, again everything is changed and center distance is calculated. Now we get A equal to 29.5 centimeter, which is little bit higher than the A minimum value, so our design is safe. Next, step 5, calculating sliding velocity. Page number 8.44, Vs equal to V1 by cos delta. This is given, and V1 equal to pi dn by 60. And page number 8.43, D1 equal to Q into Mx, formula is being given. So D1 equal to 11 into 1 centimeter. So 11 centimeter. So sliding velocity equal to 8.29 meter per second divided by cos 10.3. That is equal to 8.48 meter per second. Next, step 6, calculation of phase with B. From page number 8.48, for Z equal to 2, there is a formula B equal to 0.75 D1, and which is equivalent of 0.75 into 11, that is equal to 8.25 centimeter. Next, step 7, length for calculating length of worm. Page number 8.48, there is a formula for x equal to 0, length of worm L greater than or equal to 11 plus 0.06 z into mx. So L equal to 11 plus 0.06 into 48 into 1, which is equivalent of 13.88 centimeter. And allowance equal to 40 mm for mx equal to 1 centimeter. So length of worm equal to 13.88 centimeter plus 0.4 centimeter, which will be equal to 14.88 centimeter. Next steps 8, checking of induced stress. Page number 8.44, you can see sigma c, that is equal to 540 divided by zq, which is into multiply by square root of z by q plus 1 whole cube into design mt, which should be less than design sigma c. And all the parameter values are known, and for module and center distance we have to take new values only, and if we substitute we will get sigma c equal to 12.67 kg per centimeter square, which is less than design sigma c, so our design is safe. Next, page number 8.44 for calculating and checking sigma b values. Sigma b equal to 1.9 mt design mt divided by mx cube qz yv, and all parameter values are known to us. Now it is readily available also. So if we substitute, we will get sigma b equal to 120.5 kg per centimeter square, which is less than maximum allowable bending stress sigma b. Next step 9th, heat generated and heat dissipated. Page number 8.52, Hg equal to 1 minus eta into power, that is the formula, and 1 minus 0.82 into 12 into 10 power 3, that is equal to 2160 watts. And another formula, Hd equal to HCR into delta T into A, that is equal to Hg equal to 2160 watts. And in this relationship, HCR means being given, delta T also being given, and A is not known. Hg equal to 2160 watts we calculated. So only thing unknown is A. So capital A equal to 5.4 meter square. Next step 10th, for calculating efficiency. On page number 8.49, there is a formula, eta equal to, efficiency equal to tan gamma divided by tan gamma minus rho. Tan gamma already we calculated as 10.3, and rho value we have already, rho is nothing but using graph on vertical line mu equal to tan rho. For phosphor bronze and corresponding to the sliding velocity, we have to trace the curve, and for the sliding velocity of 8 meter per second, 8.48 meter per second, if we trace the curve, mu value can be obtained as around 0.02. Mu is nothing but mu equal to tan rho equal to tan 0.02, so rho equal to 1.14. And if we substitute in this equation available on page number 8.49, we will get efficiency equal to 89.8 percentage, and it is also uh, good. Design is good. uh, in the problem we have been given a limitation 80, only 80, minimum 82 percentage is required, but we got 89.8%, so our design is perfectly safe, perfectly okay. Thank you.